Up till now, we've been arguing heuristically about source coding. I basically gave you an optimal source code, and we sort of looked at the properties of that code without delving too much into the mathematical details. Well, now we'll look at our first serious results from information theory. So, what I'm going to talk about today is relative entropy. So this is a concept that comes up over and over. It's also known as the Kullback-Leibler distance. And basically what it represents is the distance between two probabilities, or between two probability functions. So, for example, if I have a coin, if I have a random variable x is a coin, x can take values in heads or tails, or for convenience, we'll represent that with 0 and 1. So if I can have one probability function on x, which is the fair coin, so I can have uh, 0.5 if the coin toss is heads, and 0.5 if the coin toss is tails. Or I can have a different probability function, which is some unfair coin, let's say, where the probability of heads is 0.8 and the probability of tails is 0.2. So what the Kullback-Leibler distance does is it relates these two probability functions to each other by giving us a distance between them, or some metric of the distance between them. Okay, so let x be a random variable. And let's let p of x and q of x be probability functions on x. Then the relative entropy, which is written d, p, then two parallel lines like this, q, is equal to the sum over x, p of x, log p of x over q of x. From now on, I'm going to omit the log subscript, unless otherwise specified. Log, by log I mean log base 2, always. Now, the order is important here. So, d of qp, basically everywhere there's a p, I put a q, and vice versa. Like so. And in general, d of pq is not equal to d qp. So it's actually misleading to call this a distance, because usually when one talks about distances, they have the property that the distance from A to B is equal to the distance from B to A. So for instance, the distance from Toronto to Kingston is equal to the distance from Kingston to Toronto. Not true here. So this isn't a true a true distance in the sense of a metric space. But for some reason, people call it the Kullback-Leibler distance, even in spite of that. So the theorem we want to prove is the following. dpq is greater than or equal to 0 with equality if and only if p of x equals q of x for all x. So, at the very least, it does satisfy the positivity requirement for distances. In other words, the distance from A to B is always positive. That makes sense. You wouldn't expect the distance from Toronto to Kingston to be some negative number. Distance is always positive. Excuse me. Proving this, in order to prove this, we need to go through another fundamental information theoretic result, which is called Jensen's inequality. So, why am I bringing this up now? For one thing, we just talked about entropy. This is a form of entropy. And we're also going to touch on, we're touching on some very fundamental information theoretical results that